Okay, so the last class we were talking about the performance metrics that will quantify the quality of the link, and we said the two critical parameters that will decide the performance of a link are bit error rate and receiver sensitivity. We went into the details of defining these two, and we tried to correlate the we try to calculate the bit error rate through calculation of error probability, and we wrote down the explicit expressions for the error probability of receiving a 0 given that you have transmitted a 1, and the probability of receiving a 1 given that you have transmitted a 0, and we wrote it in terms of complementary error function, and finally defined the probability of error or the bit error rate as this number, where ID is the decision threshold. Now, we went a little bit further to identify what that the decision threshold should be in an ideal scenario, because the bit error rate is depending greatly on the decision threshold. And what we realized is that to minimize the bit error rate, the decision threshold has to be chosen such that you are making your decision at this point where so the x-axis is probability again and y-axis is your received current, where the two probability curves are matching. That is when you would have minimal bit error rate. We are also assuming that the noise in the 1 and the noise in the 0 are identical in this case, right. So, this is all in the thermal noise limited condition. And we did a little bit of math to show that the optimal decision current, this could be voltage also, you can write this in terms of voltage or you could write it in terms of current. That is decided by sigma naught and sigma 1, and when sigma naught is equal to sigma 1, your ID is I1 plus I naught divided by 2. And you also define something called as Q, which is ID minus I naught by sigma naught, or I1 minus ID by sigma 1. Well, this definition is true only when you have thermal noise condition limited operation, otherwise these two numbers may turn out to be different because sigma naught is different from sigma 1. So, you define Q in that case is explicitly I1 minus I naught by sigma naught plus sigma 1, where I1 is the current corresponding to the peak of the probability for detection of 1, and I naught is the current corresponding to the peak of the probability of detection of 0. Okay. This is where we stopped yesterday, and now we want to link bit error rate with Q, because in a measurement I will know probably I1, I would know I naught, I would know sigma 1 and I would know sigma naught. The question is, how do I now define this to our performance metric? You remember your performance metric is bit error rate, right. So, to do that we go back to the definition of Q, which was ID minus I naught by sigma naught, and I go back to the definition of we had partly derived what the bit error rate was, and that was sum of these two probabilities, and we had written the sum of these two probabilities as the complementary error function, right. That is where we did a detour to find out what this ID should be. Now that we have found where is the optimal ID, I just substitute this ID here, but you will realize that this ID minus I naught by sigma naught and I1 minus ID by sigma 1 is nothing but Q, and there is a root 2 factor extra here. So, this is simply Q divided by root 2, right. This 1/4 became half because you had two contributions and both these contributions are identical. So, this gives a very nice relation between bit error rate and Q, and this is probably the most often used relation by all the system engineers. Once you know the Q, which is a measurable quantity, you can estimate what the bit error rate is without really counting the number of errors. So, the relation is so powerful that if I receive a set of ones and zeros, right, and they are noisy, a noisy set of ones and zeros is what I receive, all what I need to do is just to do a statistics to find the probability of receiving a 1, probability of receiving a 0. From that I get my I1 and I0. I measure my sigma 1 and I measure my sigma 0. From that you know what your Q is, and once you know your Q, you don't even have to do a decision to estimate what your bit error rate ought to be. If you know the Q is a certain number, the bit error rate can be predicted, and this is what most of the practicing communication engineers would do. They try to measure Q and from that estimate what the bit error rate is going to be. We can try to plot this and check so that we get some thumb rule for what should be your Q to get a specific bit error rate. Last time we discussed the desirable bit error rate in a on-off keyed system is, you remember the number? 10 power minus 9, right? So now we can see what should be the Q so as to get a bit error rate of 10 power minus 9. So this is the plot where I have plotted this complementary error function, and it turns out that this can be, complementary error function can be approximated to an exponential function provided your Q is greater than 3. If Q is greater than 3, this is true, right? So which means somewhere larger, this curve is accurate for this range of Qs, right? And it turns out that as your quality factor increases, now you can understand Q is I1 minus I0 divided by sigma 1 plus sigma 0. So larger quality factor would mean that I1 is well separated from I0, so you are able to distinguish between the high and the low. And larger Q would also mean that the noise in sigma 1 and noise in sigma 0 is going to be low, right? So both are indicating good quality of your transmission. And as your quality factor improves, the probability of making your error has to go smaller and smaller, and that's what is indicated here. And it is interesting to actually note down certain numbers. 10 power minus 9 is what is expected for a communication system, optical communication system, on-off keyed system, and the corresponding Q requirement is 6. There is also a standard which talks about 10 power minus 12. So people either try to achieve 10 power minus 9 or they try to achieve 10 power minus 12. Obviously, BER of 10 power minus 12 is a much better reliable system than 10 power minus 9 system. So if it's 10 power minus 12, the required Q is 7. So these two numbers are worthwhile remembering. Q is equal to 6 implies a BER of 10 power minus 9. Q is equal to 7 implies a BER of 10 power minus 2. So a practicing communication engineer is just going to measure Q, and if it is lying between 6 and 7, he says, okay, this system is accepted because the BER ought to be this number. You don't have to measure or do a decision for 10 power 12 or 10 power 13 bits and then find out what the number of errors, nothing of that sort is required. Now the next performance metric was, the first performance metric was bit error rate. The second performance metric was something to do with the receiver, which is receiver sensitivity. Okay. So now we will try to quantify the receiver sensitivity. As far as the English word goes, receiver sensitivity, if you look at the receiver, the English word would mean that this is the minimum power that the receiver can detect, but or the photodetector can detect. But we define receiver sensitivity in a slightly different context. Receiver sensitivity is always the minimum optical power required for achieving a certain BER. It is not that you have to just detect it, you have to also meet a specific requirement of BER. So that's slightly different from the intuitive meaning of the word sensitivity, right? So in a system, as far as an optical communication system is concerned, whenever we talk about receiver sensitivity, it is a minimum power required to achieve a given BER, and this given BER is usually 10 power minus 9 unless it is specified. So you could do it either for 10 power minus 9 or you could do it for 10 power minus 12. These are the two commonly used required BERs. So how do you do that now? Again, we could do this for a thermal noise limited system. So you start from Q, I1 minus I0 by sigma 1 plus sigma 0, and then you say it's thermal noise limited, and also that you are not receiving any power when your bit is 0. So in your receiver you have this I0, let's say it is equal to 0 power, which means there is no dark current, it's close to 0, and this is I1, right? And if I substitute this here, if I put I0 is equal to 0, this is 0. Can I cancel out I0, sigma naught? I cannot, because even though I am not receiving a power, there is going to be thermal noise. Only the short noise is going to be 0. But we are considering thermal noise limited operation, because most of the direct detection communication system operates in the thermal noise limited condition. So in that case, the sigma 1 and sigma naught are equal. So in which case your Q is equal to I1 divided by twice sigma T. So I am just putting it as square root of sigma T square, because we know what sigma, the variance of thermal noise is. Now I1 is nothing but the current when the signal is high. So a corresponding optical power is what I am referring to as P peak. So your current is nothing but the responsivity of the detector multiplied by the peak power. So when we talked about SNR also, we discussed this. We can talk about SNR peak or SNR average, right? In a system, when you say SNR, if you do not specify, what it actually implies is SNR average. So it is usually typical to represent everything in terms of average power and not as peak power, because what a detector measures is, unless you use a very high bandwidth and you are able to distinguish the power at the high or low, on an average, or you are checking the health of the system, you would always use a photodetector and it will have a very large averaging time. So what you would be measuring is an average power. So in that sense, even if you are trying to measure signal to noise ratio on a spectrum analyzer is not going to distinguish between your 1 and a 0. It is not fast enough to respond to your 1 and a 0. So the SNR is in the average sense, okay. So there were some questions earlier also when we were discussing the tutorials. When you say SNR, should it be peak or average? And unless you specifically mention, SNR is always in the average sense. So if I write this in terms of, because now here I am talking about only I1, I have to now say that this is corresponding to the peak power, and for a non-return to 0 50% duty cycle, your peak power and average power is related as P peak by 2 is your peak average, P average. So I can replace this with P average. So your Q is nothing but RD times P average divided by the thermal noise standard deviation, right. So you can now define sensitivity. Sensitivity is the average power, remember minimum optical power. So sensitivity is the average power, and you have just inverted this relation. So it is Q times sigma T square, square root of sigma T square. So this is the this whole thing represents the standard deviation of thermal noise divided by RD. And usually for 1550 nanometer, the responsivity is close to 1. So I can even say that P average is Q times approximately sigma T. So that's a very simple enough relation. So finally, the system engineer now can say that depending on the bandwidth, you have a certain thermal noise standard deviation. Depending on your requirement of BER, so if your BER is required is 10 power minus 9, I know my Q is going to be 6. My required Q is, desired Q is 6. So I know what is the average power that should fall on the receiver so that I get this BER. Okay. So that can be calculated for a given BER or given Q. So that completes the discussion on receiver sensitivity. Now the question is, one more thing we need to remember is there is no holy number for receiver sensitivity, simply because this number that we will calculate, Q and sigma T, is not specific, or it's not a given number for a receiver. It's going to change when your requirement, let's say you keep a requirement of 10 power minus 12 or 10 power minus 9, Q is constant. But the sigma T is a number which is going to be dependent on your 4 kT by R, and R is decided by your bandwidth, and also there is also an explicit dependence on square root frequency, because sigma T square is proportional to the bandwidth, sigma T is proportional to square root of bandwidth. So which means that the receiver sensitivity is going to increase as route bandwidth, which means that to get the same Q, the power required for a high bandwidth system is going to be higher. Higher by what? So, let us compare a 10 gigabits per second system and a 40 Gbps system. Can I use the same receiver for 10 Gbps and 40 Gbps system? Obviously, I have to change the bandwidth of the receiver so that it can receive 40 Gbps system. But the additional constraint is also that the sensitivity of the receiver also has to improve. I cannot simply use the same receiver because my requirement for Q has not changed. That is remaining as 6 or 7 as per the link requirement. But my because my thermal noise has increased, my average sensitivity has increased. So, this is a critical point to be considered when you are trying to upgrade existing links. Some of the links may be working at 2.5 gigabits per second. You may be trying to see whether this can be upgraded to 10 gigabits per second. Maybe the same receiver can be used. Maybe you can fit in some additional electronics. The transimpedance amplifier can be changed and so on. But what you need to also verify is it respecting the required Q by calculating the sensitivity. So, the link budget changes, the amount of power. So what does it mean? Let's say if let's do an example. Let's say that there is a 1550 nanometer receiver with a responsivity of 1 ampere per watt, typical thermal noise of standard deviation 100 nanoampere, right. Now, this 100 nanoampere is calculated for a certain bandwidth, okay. So, for that bandwidth it is 100 nanometer. Let's say that bandwidth is 10 gigahertz or something, right. So, what is the sensitivity if you were to have a BER of less than 1e minus 9, which means the required Q is at least 6. So, if the required Q is equal to 6, then the sensitivity is, you just follow the same formula. It is a very simple substitution. You say that minus 32.2 dBm is the power required at the receiver, so that I can get a BER of 1e minus 9. Why is this number important? This is how you are going to decide how to how to optimize the length of the link. So, you will say that you will start saying the link design by saying that I want to operate at, let us say, 10 Gbps. That fixes my delta F, that fixes my thermal noise, and I also say that I want to operate with a BER of less than 10 power minus 9. So, that fixes your Q, and once your Q is fixed, your receive power is fixed, which means that at the receiver you are going to demand that minus 32.2 dBm of power is definitely required. And then you can now either design what is the, so depending on what your constraints are. Sometimes your constraints may be that you have to necessarily operate for a certain length. Sometimes your constraint may be that the length is variable, I just want to make sure what is the largest length possible, right. So, depending on the situation you have, this is a very important information that you need to decide the length of the link, right. So, let us say you are going to use a fiber and let us say your transmitted power is limited by 0 dBm. Typically, the total transmitted power is limited by 0 dBm, and the reason for that is you do not want to get into the nonlinear regime of operation in a fiber. We will talk about nonlinear regime later, but 0 dBm is a very reasonable number to be used for the output power of a transmitter. Now, you have this information. Now, you can find out what is the length of the fiber that can be used in the link, because you know the loss in the fiber, without having a repeater, right. So, in this particular case, you can find out the length of the fiber as what is allowed loss. You want at least minus 32.2, you have 0 dBm. So, how much loss can you allow? 32.2 dB of loss can be allowed. Now, can I say that all that loss can be taken by the fiber? No, I have to give provision for some splice losses, right. So, let us say there are 5 splices I mean why 5? I mean depending on where you are going to lay the link, there could be 5 splices, there could be 10 splices, and let us say each splice is giving you a 0.1 dB loss. So, the splice loss is 0.5 dB. So, your loss margin for the fiber is the total loss margin was 32.2 dB was what was allowed, out of which you are allocating 0.5 dB for the splice losses. So, the loss margin for the fiber is 32.2 minus 0.5, which is 31.7 dB, right, 31.7 dB. And you know that the fiber loss is 0.2 dB per kilometer, which means you can find out what is the length of the fiber. The longest length would be 31.7 divided by 0.2, 158.5 kilometers. So, you can go all the way up to 158.5 kilometers without having a repeater. But what if you want to go beyond that? Suppose you want to establish a link which is 400 kilometer long. All what it requires is an amplifier in the middle, so that you can now start respecting the required. So, what I am trying to say is that this received average power, the receiver sensitivity is probably the most critical point at which you start your link design, right. So, you start asking this question, what is the data rate, what is the required BER. From that you can start working backwards as to what should be the transmitted power and so on, okay.